Hi, everyone, and thanks for joining me today for episode 866 of the People Behind the Science podcast. Today, I am excited to reshare our conversation with our guest, Dr. Ted Bergin. Listeners, Ted is an astrochemist who is interested in understanding how and why stars, planets, and living organisms came to be. He examines the formation of stars and planets to better understand the origins of Earth and life on Earth. And since the newly forming stars and planets he studies are so far away, Ted uses astronomical techniques to determine the presence and abundance of the molecules needed to form living things. And in our conversation, Ted shared some great stories about his life and his research. So listeners, get ready to meet another one of our fantastic people behind the science.
Every day, discoveries are made that will change our understanding of the world around us. Dr. Marie McNeely is here to bring you the brilliant minds who are making these discoveries so they can share their incredible stories and take you on an amazing journey. Welcome to People Behind the Science.
Hello, everyone, and welcome to another episode of the People Behind the Science podcast. Listeners, today I am excited to introduce you to our guest scientist, Dr. Ted Bergin. So Ted, welcome to our show. How are you?
Doing fine today. Thank you.
Wonderful. We are excited to have you with us and excited to learn more about you and your work. But before we jump in, I do want to tell our listeners just a little bit about who you are. So listeners, Ted is professor and chair of astronomy at the University of Michigan. He completed his undergraduate training in astronomy at Villanova University, and he was awarded his PhD in astronomy from the University of Massachusetts. Before joining the faculty there at the University of Michigan, Ted worked as an astronomer and astrophysicist at the Harvard-Smithsonian Center for Astrophysics. He has been awarded the University of Michigan Henry Russel Award for his exceptional scholarship and teaching, and this is the highest award given to assistant professors there at the University of Michigan. And listeners, Ted is here with us today to talk about his experiences in life and science. So Ted, we want to get to know both you and your work. So can you start by telling us what you like to do when you're not doing science?
Well, I love to spend time with my family. Being a scientist can be sometimes all-consuming. Your work can come home with you at all times. It never turns off, actually, because your mind is always thinking about the next best thing. And so I like to separate things somewhat. And so when I go home, I try to be present and be with my family. I have 2 young children, and whatever they want to do, I'm happy to enjoy and have fun with them. I'm learning guitar. I have a tutor. That's a lifelong dream, and we'll see where that goes. Not very far yet.
That's awesome. So what kind of guitar music do you like?
Old school 70s rock and roll. So I really want to learn how to play George Harrison. You can go from there in any direction, but trying to learn Here Comes the Sun, That one's really, really hard.
Yeah.
really, really hard. But I'll get there. I figure it's sort of a 5-year plan. I'll take stock in 5 years.
I like it. I like it. You've got all the steps laid out. This is perfect.
That's right.
Now, you also mentioned that you have 2 young kids. What are their favorite activities these days?
My oldest child's favorite activity is looking at her phone. She's a teenager. That's pretty much what all teenagers do, as far as I could tell. But her passion is journalism, which is quite the profession today. So it's exciting, actually. Journalism is having a sort of resurgence at present. So she gets to live in this time, which has other issues, but she gets to see all that, and that can motivate her. And my youngest daughter, she's 9. She loves to be creative. So her camp gave an award for her, called her the Creativity Monster.
That's awesome.
That's just lots of fun to see what she comes up with and does.
I love it. Well, Ted, great to hear more about you and your family. And I know we've talked a little bit about who you are and what you're doing today in terms of your current position, but I'm curious to hear a little bit more about your work. So can you tell us how you describe it to someone who might not at all be familiar with astronomy?
Sure. So more broadly, what I try to figure out why we are here. We more specifically as just life in general, and that can be the single cell bacteria, onward, upward to complex life. It's a difficult problem for an astronomer, right? Because I'm looking out at stars and planets and everything that are so far away that we can't touch them, we can't feel them. So you have to take everything we know about life on our planet and information in our solar system and synthesize chemistry, biology, geology, earth sciences, geochemistry, geophysics, and then try to pull in astronomy. So I guess the broadest way to frame this is I don't know how the first atoms or molecules on the Earth got together and made an organism that reproduces itself, right? So that's the key step for life, is a reproductive chemistry. We just call that biology. But what I can do is try and ask, well, how common are the essential materials out there in the universe? So the essential materials, one would be water. Well, where did water come from? Water is not a preordained state. It's not guaranteed that a planet will be born with water. And the same goes for the other essential materials of life. We could just pick the most abundant elements. Well, there's carbon and nitrogen. If we look at the amount of material that was present in the area where the Earth was born, the Earth captured only 1 in 10,000 carbon atoms. And in nitrogen, it's even worse. It's 1 in 100,000.
Oh, wow.
Oh, my, right?
Right.
So how are we here despite that? So whatever this process is for making the Earth, we have actually very little water. We have very little carbon. We have very little nitrogen. Yet we're here. Okay, well, that's an important statement, actually. It doesn't take much compared to what's cosmically available for us to somehow be here. But how common is that? And how can you try to use astronomy to walk back that picture? So the stuff that the Earth is made of, can I follow that back in time? And that's what we do in astronomy. I can't turn the clock back on the Earth. But what I can do is look out there today and try to find solar systems that are in the process of being born. And I can try to study their conditions. And then I can look even earlier than that to the conditions that existed before the solar system was born. There's a cloud of gaseous particles with tiny little solid state particles. They're mostly silicates. You can think tiny little grains of sand, smaller than the width of a human hair, that eventually will get together in a gigantic party and make a planet like the Earth and grab some of the gas along the way to have the water and the carbon and the nitrogen. So what we do is we look at different objects at different stages of their formation and use that to work back time and understand essentially the ultimate origin. How often are the materials of life available when a planetary system is born?
I love it. Well, Ted, you are answering some exciting big questions in your research group today. And I think that can be inherently motivating in and of itself.
Yes, it is.
Yeah. But there's some times where you feel like you are trudging through life as a scientist. Like you said, it's hard to turn it off. There's a lot of work to do. And I'm always in search of a little extra dose of motivation myself. So do you have a favorite quote or a saying or a force that really keeps you going?
Yeah, so I'm an aspiring Buddhist, and one of the things you learn is to try and focus on the now and not focus on the past or what might be in the future. So the quote that I keep in the back of my mind is, the mind is everything, what you think you become. So you just try to be focused on what you're doing and where you are, and be focused with the people who you're with. And if you can manage that, be happy with who you are and what you are, you can hopefully lead a happy life.
Absolutely. I think that can be hard sometimes, especially in science. Your mind's racing 100 different directions.
That's right. That's the challenge.
Definitely. Well, great to hear about what motivates you and keeps you going, Ted. But I want to talk next about some of the people who might have motivated or inspired you along your journey. So do you have any mentors or role models or people that really jump to the forefront of your mind?
Well, it's very common as a scientist that you have people that have helped you along the way. My thesis advisor, his name is Paul Goldsmith, who's a scientist at NASA's Jet Propulsion Laboratory at present. What he was able to do, I noticed, was that he had a way of being a prominent scientist and working very hard. But he also had a life outside of astronomy that was important to him. And that was really motivational for me in sort of how I tried to approach being a scientist. To be successful in astronomy at some point in your life, you have to work really, 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 really hard. And what I mean by that is, at times in graduate school, I would be up until 2, 3 a.m. I'd get up early. I'm really a 9 to 5 person. Mm-hmm. I'm an odd astronomer. I don't like being up at night. Very weird. So finding a way to somehow succeed and not have to work like really, really hard all the time, that's a challenge in this field. So yes, when I was younger, my years at the Harvard-Smithsonian, I worked very hard. You have to publish a lot of papers and get your name out there. But I always try to make time for myself and for other things in life. And that's something that I think Paul pointed the way for me. And the other people, it's mostly scientists that I look towards. There was Lise Meitner. I don't know if you know who she is, but with her nephew, I believe, Otto Frisch, she's the one that figured out how uranium was breaking apart. And that opened up the atomic age with all of its attendant question marks that are associated with it. But it was an amazing point in physics. And someone who's a woman in a field that's dominated by men, but yet could succeed, that's sort of inspirational in a way. And within my own field, I'm an astrochemist, which is, I'm not a very good chemist. The chemist would tell me that I am not a chemist. And I don't know what the astronomers think. But in my field, there are two individuals that really stood out to me of people who took and found ways to meld these. One was a professor at Harvard by the name of Alex Dalgarno. He worked for the Smithsonian Astrophysical Observatory as well. And he was sort of the father of the field of astrochemistry. And he was an expert in physical chemistry and chemical physics, and then started doing astronomy and really showed how you can apply understanding of the microscopic world to the macroscopic world of astronomy, because that's what we do. Chemical reactions happening on a size scale well below what we can resolve with our eyes. But the regions where clouds of these materials, mostly molecules out of which stars are born, are bajillion miles large, right? Mm-hmm. So you're looking at the very small scale, but studying something that's huge. It's got enough mass oftentimes to make 1,000 suns. So how can you do that? And he was one of the pioneers. And the other one would be Avina van der Schock, and she's a professor at Leiden Observatory. When I was young, as a graduate student, there were people that were doing the chemistry of molecules in space. So these regions in which stars are born, they're molecular in composition, and you can just study the chemistry. How does the chemistry work? But my mind was always questioning, and I wanted to know, well, how does the chemistry change as the star is born? Does the chemistry matter for the star formation? Is it somehow important for the process of star formation? And then going to the next step, what happens in the disk of material that forms around that star? So when a star is born, it collapses, it's rotating, and it conserves angular momentum. And as a part of that, you have a star and a disk of material around it. And that disk is where the planets are born. What happens there? What happens to the chemistry there? And does that matter for planet formation? So this was taking chemistry in a different direction. It wasn't chemistry necessarily for the sake itself, but chemistry for understanding the astrophysics of star birth and planetary birth. Mm-hmm. Avina van der Schock was one of the ones who was starting to do that when I was young. And I would just pick up those papers and gobble them up because I needed to understand how I could change from being just studying why water forms to, well, what happens to it? Where does it go? And does it matter in any way?
The whole process. I like it.
Yeah.
So now, Ted, you mentioned some of these mentors, some of these people who really inspired you and kept you going on your path. But I'm curious about where your path began. Can you tell us what was your first memory of falling in love with science?
It's a good question. When I was young in the suburbs of the great city of Philadelphia, I would look out my window at night and the constellation of Orion, the 3 stars in a row, Orion's belt, would be up out of my window in the winter. And I would always look up and just love to stare at that. And when I was in school, I was in Catholic school, and those schools don't have a lot of money.
Mm-hmm, sure.
There were no astronomy classes. But in my science class, when they gave me the opportunity of choosing a project to write something about, I would write about black holes or something like that. And the same thing happened through high school. So when I was applying for undergraduate, I thought that at the time I wanted to build rockets, right? Because rocket scientist sounds so cool.
Right.
But I was always worried. I don't know why. Maybe I wouldn't like it. So I made sure that every school that I applied to for engineering had an astronomy major available. So I got into Villanova, and then I think it was the day before school started, I visited the school and they showed me the engineering school and they showed me all these great machines. And I was like, oh no, that's not me.
Oh, really?
My mind doesn't do that. I can't work on actual physical objects. I'm much more interested in sort of abstract things. So my love of astronomy just came to the fore. And so I switched over immediately into astronomy. And I walked into that department and everybody was so laid back, just trying to think crazy thoughts that I never looked back. And I explained some of my journey through talking about my mentors is that when I got to graduate school, I learned the chemistry part of astrochemistry. And then my quest really was to understand how I could apply chemistry as a tool to understand star formation, to understand planet formation. And now here I am today where I want to understand why we are here, that is, life in general.
Absolutely. So now tell us about one of these projects that you have going on, investigating why we're here in the lab that you're so excited about, Ted.
There's a couple things happening right now. One of the big things is that we, as in the United States, Europe, and Japan, along with Chile, built a $1 billion telescope in the high plains in the mountains in Chile. It's called the Atacama Plateau. So we built this telescope called the Atacama Large Millimeter Array, where it's on the order of about 60-ish telescopes that don't work individually. They work together as a cohesive instrument through a technique that we call interferometry. So essentially you can get sharper pictures of astronomical objects. We call it higher resolution. So when we were taking snapshots or pictures of planet-forming regions maybe 10 years ago, we could resolve, that is, we could see everything to within 30 AU. So 1 AU is an astronomical unit. That's 1 Earth-Sun distance. So essentially the entire solar system, by and large, almost, would be in 1 pixel of our image. That's not really good, right? If you want to understand how planets are born, you really need to get into...
You need to look a little closer.
That's right. So with the Atacama Large Millimeter Array, we can do that. So we're starting to get pictures of regions where planets are being born and being able to trace the chemistry. So what we're trying to understand is, again, follow the trail. What happens to water? Where is water? And how do we do that? Well, the molecules themselves don't sit still when they're floating out there in the planet-forming disks. They actually rotate, they vibrate, and they gain energy by banging into other molecules. So just a collision can give it energy. So it'll make a molecule rotate faster. And just like anyone, a molecule kind of likes to hang out in the ground state. You could think about the ground state being sitting on the couch with some popcorn watching TV. Mm-hmm. So when a molecule slows down, it goes from one rotational state to another. It emits a photon of light. And the laws of quantum mechanics come into play, and that photon is what we call quantized. That is, it comes out at a very specific energy, which also therefore corresponds to a very specific wavelength or frequency of light. So I can tune my telescope and detect carbon monoxide in space or detect water in space. Water is a little bit harder because we have an atmosphere that has an awful lot of water in it. So for the most part, for water, we have to go above the atmosphere and use satellites, telescopes. The Hubble Space Telescope is an example, although that one isn't easily observing water. But the Herschel Space Observatory could observe water. The James Webb Space Telescope, due to launch next year, will observe rotational emissions of water vapor. Mm-hmm. So I can follow my molecules. So that's what we do. We use the Atacama Array to take these pictures of what the molecule emission looks like. And that tells us something about where the molecules are. And so you can ask, why is there a certain distribution? And one of the things we expect in a planet-forming disk is that they're what we call ice lines. That is, it's hotter close to the star, where the star is emitting out all this energy, and it's colder further away. That makes sense, actually. the Earth is warmer than Mars is, right? Mm-hmm. Now, one of the reasons that is because the Earth has a thicker atmosphere than Mars. But at its intrinsic level, the Earth is warmer than Mars because it's closer to the sun. So if you want to think about the chemistry and the way the chemistry would work, when you transition from hot to cold, you go through a transition where something will be in the gaseous state and it'll transition into a solid state, that is an ice. The pressures are so low in these regions that you skip the liquid state. It's just a gas to solid transition.
Oh, cool.
So there would be something called an ice line. That is, since we observe these emissions from gaseous molecules, if there is an ice line, I should only see the emission from the molecule, say, in the inner part of that planet-forming disk, and I should see nothing beyond the quote-unquote ice line. And we think that these ice lines may be important for planetary birth. They may be favored sites for planet formation. We don't know. That's one of the theories that is out there right now. So we're trying to detect these ice lines with the Atacama array and understand, well, are they important for planet formation? And the other thing we could do with this emission is we can measure the total content. And we could try to measure the amount of material that is present and measure the chemical abundance. And the neat thing that we're finding is that we appear to be missing material. That is, when I try to look for where the carbon is, right? I told you I want to follow carbon and understand how it gets incorporated into Earth-like worlds. Mm-hmm. So the most abundant carrier of carbon is carbon monoxide. So when we look at carbon monoxide emissions from disk systems, we should see a lot of carbon monoxide. It's carrying an awful lot of carbon, but it's not there. It's missing by about a factor of 100. Well, where is it? It should be in the gas. Everything we know about these regions tells us it should be there. And what we think is happening is that planetesimals, or another way to think of these are cometesimals, icy planetesimals are being born, and they're getting so large that when you get too big, you don't evaporate anymore. You don't care what the temperature is outside. You're so big that the ices can still stay there. One way to think about that is comets go around the sun many, many, many times before they completely lose all their water. But why is that? Well, because they're so big, many kilometers in size, that they can keep their water even when they get close to the sun, even though it's so hot. So they lose some water as they go, but they don't lose it all. So we think we're witnessing the beginnings of planetary birth, essentially. That is, these tiny little icy particles are getting bigger and bigger and bigger and bigger and bigger until they're kilometer size, many kilometer size, and eventually they're going to make things like Pluto and objects in what we call the Kuiper belt. That's the outer icy belt in our solar system, where we know that there are many objects, several objects that are the size of Pluto or even larger. And we think we're witnessing the birth of those types of objects. That's really cool.
This is remarkable. So now, Ted, I have what is probably a very naive question, but the universe is enormous. How do you know where to focus, or how do you choose where to focus this array?
So there I have to thank my astronomical predecessors. When this field opened up, it's called the field of radio astronomy. It happened after World War II. There was an excess of radar dishes lying around that they didn't quite need as much as anymore. And people took these things and tuned them to radio wavelengths, pointed them up at the sky, and discovered that the sun emitted at radio wavelengths. The center of the galaxy emitted at radio wavelength. So they started surveying the sky. The other thing that happened is in the 1970s and early 80s, astronomy became a pioneer in developing what are called charge-coupled devices, CCD cameras, to take pictures of the sky. Everyone listening is familiar with these devices because they make up a key component of the camera in your phone. And astronomy was a key part in the development of that because we want to take bigger and bigger pictures of the sky. And when stars are born, we have this collapsing cloud of gas and those particulate matter. The stars are born in a cocoon of that gas and that particulate matter, which we call dust, so gas and dust. And that dust gets heated up. And what does the hot dust do? Well, it releases that radiation as heat, and heat can be observed at infrared wavelengths. So we observed regions of the sky at infrared wavelengths, and that opened up the study of star formation. That is, we could study star formation by looking at that hot dust. And everybody went out and discovered all the main regions of stellar birth in what we call the local neighborhood, the regions around the sun that are kind of close, but we're talking astronomical distances.
Numbers beyond what I can imagine. Yeah.
That's right. So we have done lots of surveys over the past, say, 30, 40 years so that we know where to point our telescopes. We don't know all of them, actually. We still have more discovery to do. But the closest ones we found, and why do we care about the closest ones? Well, the closer an object is, the sharper an image we can take. Mm-hmm. So let's just explore that thought. The nearest region where we have one of these planet-forming disks, it's an object called TW Hydra. It's at about 60 parsecs of light. So 1 parsec is about 200,000 Earth-Sun distances. So 60 times 200,000 Earth-Sun distances. That's pretty far. The next most closest region is about 120 parsecs, about twice as far. So in TW Hydra, we can take a picture that has a resolution of about an Earth-Sun distance, whereas these more distant regions, it would be like 2 or 3 Earth-Sun distances in 1 pixel of our camera.
Gotcha.
So you not only want to find where these regions are, you want to find where the close ones are.
Well, that makes wonderful sense to me. I appreciate your very good explanation of that. But I know, Ted, you can't be making cool discoveries about planetary formation every day. There has to be some downtime in science, some challenges, some struggles, some problems that you work your way through. And I think every scientist has stories of these occurring throughout their career. So do you have one of yours that you'd like to share with our listeners today?
I couldn't relive those struggles. So the beginning years of studying astrophysics in college and graduate school, you can go into an exam and walk out of that exam and get maybe 4 out of 10 of the problems. Mm-hmm. And actually you go into the exam and some of them you're like, oh my God, I have no clue how to do that. And I'm honest about that. There were times where I really got my butt kicked and it was really, really hard. So what I had to do was buckle down. You could say study harder, but I had to draw upon the reserves of people around me, my fellow students, or go talk to the professor and have them help you understand how to do things. So I remember when I was learning quantum mechanics, I was probably fail in the class. This was in graduate school. And so I went and I talked to the professor and I met with him probably once a week and tried to figure out what are the concepts that I'm not understanding and why. And I was able to pull my way through fine, thankfully. But it wasn't easy. So that's always the hard part in life, when you find yourself failing. And sometimes you may even reach your own limit. So I'll tell you straight out that I am not going to solve the problem about how Earth is born, 1, by myself, and 2, I probably won't even solve it at all. But what I can do is work with others in other fields. Right now I'm working with some geophysicists to try and understand what happens when you supply material to an Earth, material that has carbon or water or nitrogen in various organic forms. What happens to that material? We need to talk together. The astronomers have to talk to the chemists. If you want to understand how the Earth is born, we have to talk to the Earth scientists. They've been studying it for years. We each have something to bring to the table. We can solve things together. We are not going to solve the complete problem, but maybe we can figure out what the most important parts are and focus our efforts on some of those and understand how they work. And so we can get a step in the direction of understanding why we are here. So I think that's the other thing that I've learned.
Definitely. Well, I'm so glad, Ted, that you shared this story today, because I think it has a really important message, the importance of drawing on the knowledge and the expertise of others, and especially for young scientists out there who are listening. Don't be afraid to ask for help. Generally speaking, your professors want you to succeed, and they will kind of bend over backwards to help you get there and help you understand it.
That's right. That's what we're here for.
That is your job. Yeah.
That is what pays the bills. And it's also a passion, right? I'm a scientist. I want everyone to understand and look at the world and see how amazing the world is when you look at it and say, hey, I think I know how that works. We just had an eclipse, right? Mm-hmm. That was a wonderful, wonderful moment to share my love of astronomy with anyone.
Absolutely. Well, like I said, I'm so glad you shared the story, but we don't just want to talk about your challenges, although it looks like things turned out well for you here, Ted. But I do want to talk about successes next. I know success in science comes in many different forms, big and small. Do you have a favorite success you want to share with us today, Ted?
Sure. One of the things I've been trying to do is understand, as I said, what are the chemical abundances in a planet-forming system, so that I can follow the carbon or follow the oxygen, follow the nitrogen. It actually turns out that it's kind of hard because in astronomy, we measure abundance by looking at taking things relative to hydrogen. Hydrogen is the most abundant element. Makes sense, right?
Yeah.
But it turns out that through a quirk of nature, hydrogen in molecular form doesn't emit or tell you that it's there in the conditions of a planet-forming disk. It is too cold. The temperatures throughout much of the disk are only about 20 to 30 degrees above absolute zero. That's minus 400 degrees Fahrenheit, so cold. Mm-hmm. There's not enough energy there for a hydrogen atom or hydrogen molecule to gain and actually emit a photon and tell you it's there, so you can measure how much of it's there and measure the actual mass of the system. Mass is so crucial to astronomy. Why? Because of gravity, of course. The more massive things are, the more likely it is that gravity will take hold and be an important component of the evolution. So how can we do it? How can we measure the total content so that we can get our abundances? It's really, really hard. So I had this idea that we could maybe use what we call an isotope or an isotopologue of hydrogen deuteride. So deuterium is the same as hydrogen, just a little bit different. So hydrogen has a proton and an electron. Deuterium has a proton, a neutron, and an electron. So it's still a hydrogen because it has that one proton, but it's a little bit heavier. You may be familiar with this concept of deuterium in a molecule when we think of heavy water. Mm-hmm. That's something you might have heard of with respect to nuclear reactors. Heavy water is, instead of having the hydrogens, you have deuterium atoms substituted. So hydrogen deuteride, we might be able to detect it in a planet-forming disk. And if we could maybe measure the mass, since I actually kind of know how much deuterium is present, thanks to, again, my wonderful astronomical predecessors who've gone out and measured the relative amount of deuterium to hydrogen in interstellar space. Neat little aside, all the deuterium that we have in the universe was created in the Big Bang, and we haven't made any since.
That's amazing.
That's kind of neat.
Yeah.
So the problem with hydrogen deuteride is, one, you can't observe it from the ground. You have to observe it from space. And two, I don't know if I can detect it. So I am what I would call fishing. And I was gratefully lucky that my colleagues who were judging proposals for the Herschel Space Observatory, which operated for a few years, about 2010 to 2013, give or take. Herschel was an ESA, European Space Agency mission that had NASA participation. So Americans took part in the science of that observatory. So I was lucky. They allowed me to fish, and I detected hydrogen deuteride in that closest planet-forming disk. And ever since then, we've been using that as a way to get at mass and way to get at abundances and tell what actually is going on. I need that underpinning because I'll never know if I see less of a molecule there, whether it means there's less of just that molecule or less of every molecule, right? You can think about it this way. If I have a mass and the mass is a factor of 10 lower, that means there's a factor of 10 lower of everything. Mm-hmm. Or I could just have a factor of 10 lower of one molecule, i.e. chemistry. I need to know the mass if I can understand the chemistry. Sure. And if I want to track things and understand the chemistry of planet formation, this is crucial and fundamental information. And I got very, very fortunate that we were able to do that and perform that experiment, and it was successful.
Well, congratulations, Ted, on this success. And I love this story of success because a lot of times scientists, I think we poo-poo these sort of fishing expeditions, or you sort of look at them less favorably than the hypothesis-driven work, but I think some amazing discoveries come out of them, and this is just one example. So it's been great to chat about your work, but I want to talk next about what you're reading, Ted. I love getting book recommendations from all of the guests that we have on our program. So do you have a favorite book that you can recommend for me and my listeners today?
Sure. So I'll have the baseline, which of course is I read Tolkien about 60 times when I was a kid. So The Lord of the Rings was a key component of my existence. But there's a wonderful book on tracing the earliest fossils of life by William Schaff called The Cradle of Life. And if you want to work back as to when life began on the Earth, it's really difficult work because we don't have many rocks that go back 4.6 billion years. The oldest rocks we have maybe go about 3.8 billion years or so. And a lot might have happened to those rocks in that time. And it's very hard to find fossils, but they have evidence for these sort of microscopic fossils that may or may not be some of the earliest tracers of life on our planet. There's quite a debate about that. But that was a wonderful book and a nice story of a scientific journey within a wonderful framework.
Awesome. Well, I will put both the Lord of the Rings series and The Cradle of Life on our website for our listeners if they're searching for a book recommendation, Ted. So thank you for that. And we've talked about some different aspects of your career, but one thing we haven't really touched on is travel. And I love talking to scientists about all of the wonderful places that their work has taken them. So Ted, do you have a favorite place that you've traveled for science?
Yes. Several years ago, I had the tremendous fortune to go to Iceland. We were having a tiny little workshop, 20-ish people, about the origin of water on the Earth. And the organizer, Professor Karen Meach of the University of Hawaii, had this great idea to go to Iceland. And oh my God, the island, right, is basically the tip of a volcano. And you can see the layers of different volcanic events that led to the formation of one particular rock outcropping. And then everywhere there's fjords, and you couldn't shake a stick without finding a waterfall. It was so outstandingly gorgeous. I guess the way to say it, it was geology front and center, the beauty of our planet. And then one of my favorite memories was sitting in a hot spring with a drink in my hand, watching the Northern Lights.
Oh, wow.
So, hey, you can't beat it.
Right. It's only downhill from there, it sounds like, unfortunately.
That's just that little problem, yes. But Paris is nice.
Of course, of course. So did you have some time to explore Iceland while you were there?
Yeah, so we were there for about a week, and we went around the entire island.
Oh, that sounds wonderful.
It was just great.
So do you have a favorite place that if our listeners are going to Iceland, that they have to see when they're there?
I would just say don't spend your time in the cities. Just drive in any direction.
I like it. Well, Ted, wonderful to hear about your experience visiting Iceland. And I think another aspect about careers in science that we love to talk about are the people that you get to work with. I think scientists are wonderful, creative, funny, amazing people. And that's contrary to some of the stereotypes that are out there about scientists. So I love to showcase these things on our program. So Ted, do you have any funny memories or maybe quirky traditions that you experienced that you want to tell our listeners about today?
I guess one of my more amusing memories is a wonderful colleague of mine, now retired, Professor Tom Phillips of Caltech. He was a wonderful man and just another really good mentor to me. He was the director of what was called the Caltech Submillimeter Observatory at the time. It's an observatory that's on Mauna Kea. It's being taken down, actually. So I was observing in this telescope, and I had a half night. And Tom Phillips, the director, was on after me. I was much younger then. So the way this telescope works, actually, is instead of the telescope moving, the building actually moves. So the building rotates, and then the telescope just does up and down.
Oh, cool.
That's kind of interesting. First, I thought I was, sort of seasick when I sort of went there first. Because Mauna Kea has its own challenges, no oxygen, all this other stuff. I could get into that and the insanity of all that. But observing at the Caltech Observatory, a submillimeter observatory, tell the telescope to go observe something, and then I go to the bathroom. And as I am going to the bathroom, the building moves. And I'm thinking to myself, I didn't tell the telescope to do that.
Oh, no.
I wonder what's going on. So, okay, I go back, I sit down. Indeed, the telescope has gone to a random spot in the sky, and I tell it to go back. And it observes or looks at that spot in the sky where I told it to go for a little bit, and then it just goes somewhere else a little bit later.
Weird.
So the only thing I can think of doing, I have no clue what's going on. I'm a theorist and an observer, but when I'm observing, I think the theorist part comes to fore. Going back to the engineering, right? I'm not very good with actual
mechanical, yeah.
So I rebooted the telescope, and it wouldn't work after that. So then I'm sitting there, and the director of the observatory shows up.
Oh, geez.
So I had to give him a telescope that was not working. I went down. I hoped he could figure out. And I heard later that he told a colleague that Ted broke the CSO.
Oh, no.
But it turned out that astronomy, to look at a point in the sky with any precision, you need to know the time because the stars move, because the Earth is rotating.
Sure.
And the telescope had just lost its connection to the clock.
Ah, it sounds so simple.
In any event, yes, I broke the CSO. Yeah. An amusing moment in my life.
That's almost terrifying, too, with the director coming in right after you.
Yep. You got to just live through them.
That's right. Well, I'm glad you survived this traumatic moment of a telescope gone rogue there, Ted. And we've talked about some of the big questions that you're answering with your research today, but I'm curious, and I think I may know the answer to this one already. But if you could ask anything, if you had all the funding, staff, technology, resources, whatever you need, what would you want to know?
Well, it's very hard to fund interdisciplinary science. If I want to get funding from the National Science Foundation, for example, to work with my geophysical friends, I have to send a proposal to two different panels where the geophysicists are looking at the astronomy and saying, what is this? And the astronomers are looking at the geophysics and saying, what is this?
Right.
And it's very difficult. So, yes, I would like funding to do interdisciplinary science so that we can make progress in understanding as to how the Earth came to be the way it is.
I like it. Well, I think it is a worthy proposal, and I wish you and your geophysicist friends all the luck getting this funded. Now, we've talked about your career journey and some of the people who helped you along your way, and I think these mentors, these people that you work with are great sources of advice. So, Ted, is there one piece of advice that you received at some point that really helped you that you want to pass on to our listeners today?
I think it's be happy with what and who you are. If you are constantly wishing you had something else or wishing you were somebody else who somehow through the gift of birth has gotten some other more intelligence, less intelligence, money, whatever, be happy with who you are. If you're not happy with where you are at a given time, you may never be happy.
A great message to pass on to our listeners. Now, Ted, is there any other last piece of advice you want to give them, or even a last note of inspiration you'd like to leave our listeners with today?
Don't be afraid of science. Science is your friend. And please just look at the world. And when you see something, ask why. That's all you need to do to be a scientist, is ask why and try and understand the world around you. It's a wonderful, wonderful, beautiful thing. Just walk out, look at the leaves on the tree and ask, wow, that's living. Why is that here? Think of all the living organisms that surround you on this planet and enjoy the wonder of it all.
I love it, Ted. Listeners, be happy and be curious out there. Ted, can you tell them if they want to learn more about you and what you do, where should they go?
Sure. My email is fine. It's ebergin@umich.edu, but I'm what I call Googleable. Mm-hmm. So if you Google for Ted Bergin, I'll come up and you can find my website that has the contact information.
Absolutely. Well, listeners, definitely get in touch if you have any questions. Check out Ted's research on his website. And Ted, thank you so much for joining us today and sharing a piece of your story.
It was a tremendous pleasure. Thank you.
Well, it was a joy to have you here with us. And listeners, wonderful to have you here as well. We'll see you next time on another episode of People Behind the Science. Your voyage to explore the lives of today's exceptional scientists has just begun. You can find everything we talked about today, including our guests' favorite books, biographies, photos, and more, when you visit us at www.peoplebehindthescience.com. I look forward to chatting with you next time on People Behind the Science.